Okay, welcome back to a new physics tutorial. In this video I would like to answer the question of an exercise that I found some time ago. So the exercise says that you have a fridge which cools down or with a height of 0.8 meter and a width of 0.6 meter, and it cools down its content to a temperature of 7 degrees Celsius. Now the question is, which torque has to be applied to the door in order to open it. So of course the question is why there is any torque required at all. So what happens is that when you open the door of the fridge, warm air from the surrounding goes into the fridge, and when you close the door it cools down, and due to the fact that the temperature changes, the pressure changes, so you get a pressure difference between the outside and the inside of the fridge. And this pressure difference leads to a force and to a torque which has to be applied in order to open the door again. And you can feel this, I think, if you have a fridge at home and you let it open for a little bit longer time and then you close the door again, you will find out that you need a really huge amount of force in order to open the door. And now we want to quantify this a little bit. And the question is actually not so difficult. It's very short. And it looks like that actually some details are missing, so it's not possible to answer it with that small amount of knowledge which we have. But you will see now throughout this calculation that actually it's enough, and we will go now through the solution step by step. So the first thing which I would always recommend is to make a sketch, as usual. So I would like to start with the front view of our fridge. So what we can do, we can draw here our fridge. Not very beautiful, but I think you can recognize it. And this has a height h, as we said before. This should be 0.8 meter, and we have also here a width, let's call that w, and this should be 0.6 meter. Okay, then we have here our handle, which should be maybe placed on the left edge of our fridge door here. And we have, of course, a hinge here, which is the rotating axis of the door. So the door rotates around this axis. So we can say the lever arm that we have between the rotation axis and also the hinge is around 0.6 meter. And then what we can also do, we can draw the top view of our fridge, which would maybe look like that. So this is when you see it from the top. And then here in front you have our door, with this handle here on the left side. And again, we have here our width, W. Then we have a temperature inside our fridge, let's call that T1. And we have a pressure inside that we call P1. And we have, of course, a temperature outside, which is room temperature, let's suppose 20 degrees Celsius. And we also have P0, the air pressure outside, which is most likely something like 10 to the power 5 Pascal. Okay, now we start with the calculation. So what we need, we have a temperature and we have a pressure. So when you hear these kind of two words in an exercise, you directly think about a certain law. We can of course use the gas equation of ideal gases, and we also assume that we have ideal gases here, but this is an overshoot in this case. So what we actually need is the law of Amontons. I'm not a French-speaking person, so I don't know whether it's pronounced correctly, because I think it's a French physicist. So if there is some French person looking, please correct me if I'm saying something wrong. But what we need is actually the law of that person that he derived experimentally, and this says that the temperature over the pressure is always a constant. So the fraction of P and T is always constant. And this means that, of course, the pressure after closing the door over the temperature after closing the door, the temperature of our fridge, has to be equal to the pressure outside over the temperature outside. So this is the only thing which we have to do, and this is when we have written down this equation, we have already solved half of the exercise, so to say. Because the only thing which we now have to do, of course, we have to solve this for the unknown variable, and this is of course in this case P1. So what we have to write, P1 equals P0 over T0 times T1. Yeah, and then we know we could calculate now directly P1, but I would like to first write down the rest and then insert this into our equation. So what we are really interested in is not P1 directly, we are interested in the pressure difference. Yeah? So what we can write, pressure difference, and this is of course delta P. And this is the temperature outside minus the temperature inside the fridge. Yeah? And because this results in the force that we measure. And now we can insert here our P1 into that, which comes maybe something like here. Yeah? And then we can also directly put this P0 out of our parentheses. So what we then actually get is 1 minus T1 over T0 times P0. And now we can insert the values that we have. So we know 1 minus, and then T1 is when we have to now insert these values in kelvins, otherwise it does not work. 280.15 Kelvin divided by 293.15 Kelvin. And then we have to multiply this, of course, still with our P0. And when we calculate this, the result would be, as I said, P0 is 10 to the power 5 Pascal. So the result is 0.00, sorry, 1 0 too much, I think. It should be 0.044 times P0. Yeah, so this is what comes out from this fraction here that we have calculated. And this would be then 4,400 Pascal. Yeah, which is quite a huge amount, as we will see also when we calculate now the force. Yeah, so in the next step, of course, as I said, we have to calculate the force because this is what we are interested in. And yeah, as you might know, the force is just or defined as the pressure times the area where the pressure difference happens, which means that we have to calculate delta P times A. And now the question is, what is A? Of course, this is our width that we have given and our height. This is the area of our door. So what we can write here is now delta P times H times W. And yeah, when we insert these values, we get 4,400 Pascal times 0.8 meter times 0.6 meter. And I have calculated this already before. This leads to a force of 2,112 Newton, which is really a huge amount. Yeah? I was not expecting this before I calculated that. So what actually happens is we have our door, and we have here from our center of gravity of that door a force acting in from the outside to the inside of our fridge with a magnitude of 2,112 Newton. Yeah, so if we would open the door just into this direction here, then we would have to apply that force in order to open the door. But luckily, yeah, we don't have to do that because this would really be problematic. The advantage of a fridge is that we have this door hinge, as I said before, and a handle with which we can open it and rotate it around a certain axis. And this actually leads to a torque. And this torque, we will see, is much easier to handle compared to the force that we have here. So what we will do, first I would like maybe to create a new page. And now we want to calculate the torque, yeah, that has to be applied. This is also the main question that was asked in this exercise. So the torque is of course generally defined as the integral over the force with respect to the lever arm, to dr. But in our case, the lever arm, of course, would be the width here that we have given, 0.6 meter. Yeah? So we have to write here integral f dw. And yeah, then we can insert our force formula that we have given before. And this was, as you remember, delta P which is actually a constant, so we can put this in front of our integral, and also the height, yeah, and then we can write here down this integral, and then only this w has to be inserted into our integral, and then dw. So this we have to solve, and this is actually very simple. So we can write here delta p h, and this would just simply give 1/2 w square. Yeah, and now we can already see what happens. So we have here our delta p, we have our h, and we have 1 w, and this we can again combine together to the force that we have given before, yeah? This formula which we have inserted here. So what this actually means is that this is 1/2 Fw. Yeah, so this is very interesting, because what it actually means is that we have to multiply this force that we have calculated before with one half of the width that we have given, and this gives then our torque. So it's actually really simple, and we have already calculated our force. So the only thing which we have to do, we have to insert that here, and we have at the end given 1/2 times, and then we have to insert our 2112 Newton times our width, which is 0.6 meter. And when you calculate all this, then you get as a result 633.6 Newton meter. Yeah, and this is also, again, still it's a quite large amount. So let's suppose you have a very light person with a weight of 600 Newton, which means that his mass would be something like 60 kg, and he stands on a lever arm with a length of 1 meter. Then this is actually the torque which is applied here, or which has to be applied in order to open the door. And I would say that if you really have to do this, it would be really difficult. Yeah. So what the companies that produces fridges are doing, they actually insert a mechanism which prevents the door of being locked in that way. Yeah, so there can be, for example, just a small hole inside the fridge, which makes it possible that there is some air exchange and pressure exchange. So the pressure difference that you get at the end is much smaller than the one which you get when you only take the gas laws into account. And this makes it at the end easier than to open the door. Yeah, but if you don't do that, then you would really require a huge amount of force and torque in order to open the door. Yeah? And I hope that this was quite interesting and instructive. I hope that you liked the video. If you like it, please hit the like button. Please subscribe my channel if you have not done so far. And hopefully also see you back soon for a new physics video.